So in this chapter, we will learn a new type of neural network called a recurrent neural network. But before we go into learning the exact details of RNNs, so recurrent neural network in short is referred to as RNN. But before we go there, let's understand the need for it, right? So first let's understand our multi-layered perceptrons. Our multi-layered perceptrons literally take X as input, right? I have an MLP here and it returns Y, right? What happens with my ConNet or my CNN? I have X, which is an image, right? My CNN also takes my image as input and returns Y, but internally it's using the convolutional structure. It's using the image because images can be convolved on, right? So it's using operators like convolution and max pooling and things like that, right? That's why the architecture of a CNN is slightly different from an architecture of an MLP because of layers like convolution layer and max pooling layer and things like that. But and CNN works very well if your input data is an image, right? And MLP works very well if your input data is a vector. If your input data is a vector of numbers, right? Now, what if, this is the big question, what if my input X is a sequence? Now you might wonder, where do I see sequences? Let's take a bunch of examples, right? Let's take a bunch of examples. The first one would be, what if your X is a sequence of words? What if your X is a sequence of words? We have been seeing Amazon food reviews, right? Remember, we have been seeing Amazon food reviews as a running example throughout this course. So you're given a review and you have to predict whether the review is positive or negative, right? Now, what do you get as input there? You get a bunch of words, right? You get, let's say, word 1, right? You get word 1 followed by word 2, followed by word 3. You get a sequence of words, right? And the sequence is important. Let's say if somebody says this smartphone, this phone, right, is very fast, right? So actually in most languages, the sequence matters, right? But when I say this phone is very fast, when I say fast, I'm referring it to the phone. When I say very here, this very is being being used in the context of the phone and fastness, right? So the sequence is important here. And you see sequences of words in lot of text, lot of natural language processing problems and text related problems in any language, not just in English. They all of them have a sequence of words, and you encounter this all the time. So whenever we encountered this, what did we do till now? So look at all the Amazon food review all the Amazon reviews, all the models that we build on Amazon reviews. What we are breaking them down is we are breaking this text into bag of words or TF IDF or some form of averaged word to vec and things like that. And when we do this, what are we eventually leading it to? We are completely discarding the sequence information. Whether the sentence is the phone is very fast or very fast phone is this. Whether the sentence is this or the sentence is this, the bag of words representation is going to be the same, because it's the same exact set of words that are present in both sentences, right? So what we're doing actually in any of our existing featureizations for text that we have learned and that we've used extensively throughout this course, we are completely discarding the sequence information. But sequence information actually is very important in natural language processing. So RNNs are one very popular technique, very popular technique, where we use the sequence information for training models, right? So this is like literally the next big leap after all the techniques that we've learned, right? So this is one thing that occurs a lot of times. The second thing that you often see is you might have time series data. You may have time series data. For example, you have some time on this axis, and you have some values on this axis, and let's assume it's following like this, and you want to predict what is the value of this. Let's say this is y and this is time, right? You want to predict what the value here would be, what is a future value, right? For that, what have we done? We have seen time series analysis, right? We would actually, the way we have done it till now is we have broken up time into intervals, right? We break up data into intervals and we take maybe last 5 time steps, right? So we basically windowed the data. Okay, we basically constructed time windows and we would take all these values. This value goes here, this value goes here, this value goes here. And based on these last 5 values, we are trying to predict the next value. Or we would move into frequency domain, right, using Fourier transforms. We have seen some of these in the previous chapters where we learned how to process time series data. But actually, time series is also a sequence information, right? Because you get one value after the other value. So you get your first x11 at timestamp 1. So similarly, x1, let's call it just x1. You have x1 at timestamp 1. You have x2 at timestamp 2. You have x3 at timestamp 3. So on xt at timestamp t. And for each of these x1s, you have a corresponding y1, y2, y3, so on and so forth, yt. And your point is, given a new xt plus 1, you want to predict what the next yt plus 1 would be. So time series prediction is also actually a sequence prediction problem, because the information is sequential, because one comes after the other, right? We have partially used that sequence information by windowing the data, right? The third thing that you often see is translation. It's called machine translation problem. This has become very, very popular application of deep learning in the recent past. Suppose if I give you a sentence in English, suppose I'm traveling. Imagine I'm traveling to Spain, right? I want to give an English sentence and I want the machine learning model to convert into Spanish, right? So what you have here is a sequence input, because the sentence that you're giving in English is a sequence, and the output that you have is also a sequence of words in Spanish, right? So machine translation is a very nice example where you have a sequence input and a sequence output. And these models are called sequence to sequence models, which are basically small variations of RNNs. So for lots of very, very interesting applications, like determining the sentiment of a review, whether the review is positive or negative, you need sequence. I mean, it's great if you can use sequence information. Of course, we have gotten around without using it, but if you use it, the models will improve dramatically. For time series prediction, be it stock market prediction, be it to predict stock market movements, or for any sort of time series. Like we saw the Uber case study, right? In the Uber case study, if you have not seen it, it might come just slightly after this. In the Uber case study, we predict, or in the New York City taxi cabs, right? Data set. What we see here is how many cabs can you expect at a given location in the future, given all the past information, which is a very, very standard time series problem. Machine translation happens a lot. The fourth application, which is very, very common again, is speech recognition. In speech recognition, I input a sequence in audio, right? If you take speech recognition is found a lot in Siri, in Alexa, in Google Now. Of course, my favorite has been Google Now till now because it's very, very accurate, right? I give a sequence in audio. It's basically audio sequence, right? And what it outputs me is the sentence in English, right? This is what all of speech recognition is all about, because audio is also a signal, right? Audio is also a signal, which is a sequence signal, and you get an English sentence, right? This is a very, very popular application. And the fifth type of application is where you input an image, okay? And what it does is it captions the image and tries to give a sentence on what is there in the image. This problem is called image captioning. So what it does is you give an input as an image. The output is basically an English sentence explaining you what is there in the image. Okay, so it provides you captioning to the image, right? So your input is just one image, but your output is an English sentence, which is a sequence, right? So these are all many, many very, very popular applications of RNNs. Actually, in all these cases today, RNNs are used extensively, be it in NLP, be it in time series prediction, machine translation, speech recognition, image captioning. These are very, very popular applications. You might wonder, why is image captioning useful? Because Imagine Google providing you image search. Look at Google image search. Image search can be improved a lot if you have an English representation of what is there inside the image, right? Because once you have the contents of the image, right? Because once you have this English sentence, it almost becomes like Google text search, regular Google, just like Google search. So Google image search can be improved dramatically by captioning each of the images into English sentence and then using the Google standard text-based search on top of it, right? Because now you know what is there inside the image, isn't it? So you might wonder, all this is great, okay, but what is so important about it? So the core idea here, the core idea here is, if your output if your output depends on the sequence of inputs, not just the set of inputs, okay, but the sequence of inputs, right? Then we need to build a new type of neural network, right? Which gives importance to the sequence information. It somehow retains the information. It somehow retains and leverages the sequence information. It somehow retains and leverages the sequence information to perform better than non-sequence based approaches, right? The next thing that you immediately get is, let's take this example, right? Let's take this example to make it concrete. Let's take our Amazon food reviews, right? Let's take our Amazon food reviews, right? Where you have literally a sentence, or a sequence of sentences, and you have to predict. So this is your xi. Your xi is a sentence. Your yi is basically a two-class classifier, 0 or 1, right? So let's assume, let's take one sequence. Let's take one sentence xi. Let's assume this sentence contains multiple words: xi1, xi2, xi3, xi4, xi5. These are words. This is word 1, right? This is word 2, so on and so forth. Then you might wonder something very simple. Since each of these is a word, let's assume the phone is very fast, right? Then you might say, why can't I just use an MLP for this? Let's try to build an MLP, a simple multi-layered perceptron, to solve this problem, right? Now, what is your xi1? Your xi1 is a word, right? It's not one feature. Your xi1 is a word. Now, I can represent this word as a one-hot encoding. So your xi1, so let's assume in my vocabulary I have 10,000 words. In my total vocabulary, I have 10,000 words. So xi1 can be represented as a vector, as a one-hot encoded vector. Right? Is this word 1, word 2, so on and so forth, word 10k? Yes, it is word 1, rest everything is 0. So your xi1 is a vector. Similarly, your xi2 is a bag of words representation of this vector. Okay, this will be 1, rest of them not bag of words, it's just a simple one-hot encoding, right? So your xij belongs to R10k. It's a binary vector. Remember, this is not a scalar, this is a vector. I'm repeating it. This is a vector. This is a vector. This is a vector. Because each of these is a word, right? So now you may say, why can't I simply train an MLP on top of it? Let's see if we can train an MLP. Let's assume I have one layer. Okay, I have another hidden layer here. My input now, what if, see, look at this. What is my sentence here? xi1, xi2, xi3, xi4, xi5. So I have five vectors of size 10k. Right? I have five vectors of size 10k. So what if, okay, this is my, let's say, layer 1, my layer 2, right? And then I have, let's say, a softmax or a logistic regression layer, and here I get my yi. Okay, it's a two-class classification, so I have a logistic regression layer. Softmax is just a generalization to multi-class, right? So my input, what I can do with my input is this. Here I have my vector for xi1. Here I have my vector for xi2, my vector for xi3, my vector for xi4, my vector for xi5. So this whole input now is 50k dimensions. This whole input is 50k dimensions, isn't it? Right? So this becomes my input. So there are, so between this layer, okay, let me just draw it slightly differently. So this is my whole input layer. This whole thing is my input layer. Now I can have a fully connected. Remember, look at this. This is a fully connected, this is fully connected, and this is fully connected. And of course, you have a bunch of activation units inside this, right? Each of them is your activation unit, your functions f. Okay, your simple. Of course, the number of neurons in each layer, you can decide that, right? But look at the structure here. You have 50k inputs here because you have 5 words in your xi. Your xi consists of 5 words. Okay, that's why you have 50k input. So you might say, okay, I'm still preserving the sequence information. The argument that some people make is, I can build an MLP like this and I'm still preserving the sequence information because the first word is the first 10,000 vectors. The second word is the second 10,000 vectors, a vector of the next 10,000 elements. My third word is here. My fourth word is here. My fifth word is here. So I'm still preserving the sequence, right? I'm still preserving the sequence by putting the first word on top of the second word, on top of the third word, fourth word, and fifth word, which is a nice argument. But there is one problem. There is one key problem with this approach, which is, imagine I have 2 reviews. Let's call it x1. Okay. Let's assume I have one review, which is, this phone is very fast, right? My second word is, this phone is good. Now your x1 has 5 words. Look at this. Your x1 has 5 words. So because you have 5 words, you have a 50k dimensional vector, because each word is represented as a 10k dimensional vector, right? As we have seen here, because your vocabulary has 10,000 words, right? Now x2 will be represented as a 40k words because it has only 4 words. So your input size is changing, right? Your input size is changing because one sentence can have 5 words, other sentence can have 4 words, other sentence can have 20 words, right? It could have 20 words. So this has 5 words, this has 4 words, this could have 20 words. Then you have 200,000, a vector of size 200,000. Your inputs, this is the key problem here. All your inputs, because they're sentences, they can be of different lengths. They can be of different lengths. Your sentences could be of different lengths. You might argue, okay, I will just, if the sentences are of different lengths, one other argument that you can make is, you can try to fix this problem as follows. You'll say, my input vector, so let's assume I have sentences x1, x2, x3, so on, so forth, xn. Okay, so let's assume this is 10 words, this is 4 words, this is 15 words, and this is, let's say, 20 words. I'll take the max of all the words that are present. Let's assume the maximum number of words is 50. So you will argue that you'll actually build a vector which is of size 500k, because the maximum number of words is 50 words. And if you have x1 with only 10 words, you'll only fill the first 10k dimensions, and rest of them you'll just give zeros. This is basically zero padding. You're actually performing zero padding on the vectors, not on the matrices. Okay, so for x1, you'll build a 10,000 dimensional vector. You'll build a, you'll build a 100,000 dimensional vector. I'm sorry. You'll build a 100,000 dimensional vector, because each word, one word takes 10k dimensions, right? So you'd argue that you'd build a vector of 100k, the rest of the 400k, you'll just give zeros. Okay, this is one fix that you can think of, but there's one more problem with this. Let's assume you have a query sentence which is 100 words long. You don't know what query sentence. This is your test data. This is all your training data. This is all your training data. In your test data, you might get a query point with 100 words, which means now you need 1000k or 1 million dimensional vector, but your vector is only 500k. So this is one problem. Even with this fix, there is this problem. Number one. Number two is, just imagine the size of the input here. This input size will become massive. This input size will become massive. In most cases, it will just be zeros. Do you really want that? You're just building unnecessarily, you're building unnecessarily. I keep getting confused with the spellings. I'm very happy that Google has spell correct. Okay, you're building just unnecessarily very, very large networks by just zero padding everything. So this is called zero padding because you're just placing zeros here. Which is, I mean, training such a large network with hundreds of thousands, with 100K, or maybe even a million input vectors is just unnecessary. Is simply unnecessary. Just imagine the number of connections you'll have. Imagine if you have 1 million inputs here, and even if you have 1,000-layer network here, just look at the number of connections that you'll have. This weight matrix that you have here, right? The number of entities in the weight matrix is going to be 1 billion. So you have 1 billion weights that you need to train because there are 1 million inputs here, and in the next layer you have 1,000 neurons. So 1 million into 1,000 is 1 billion. Imagine training a network with 1 billion neurons. It will just eat up all of your time. And I'm not cooking up these examples. If you actually try an NLP problem using an MLP, using this hack or this fix, or using this fix, it will just blow up. You can easily run into billions of weights, which will make the problem extremely hard to solve. And in most cases, you just have zeros here, right? So to avoid all of these issues, people have said, let's design a new form of network. Let's design a new network from scratch. And that network is called a recurrent neural network. We'll see how recurrent neural network solves the problems that we've seen here. There are two problems here. First is that each of your input is of different length. Right? Each of your input is of different length. And second, you just don't want to blow up the number of weights unnecessarily and make the network too hard to train. Right? In the next video, we'll understand the basic structure of an RNN. And in the next few videos, we'll understand RNNs in a lot of good detail.